In this presentation, we want to be able to identify how many of the digits in a particular measurement are significant and how do we do various types of calculations and determine how many significant figures there will be in the answer. Well, we have to determine the uncertainty in the measurement like we described previously. And so in this particular example, it's relatively straightforward. First of all, if we have a number that contains non-zero digits, so in this particular case this is 5,943, none of the digits are zeros, and that makes it straightforward. All of those digits are significant. They've been measured. So I would say that this number contains 4 significant digits. It turns out that the zeros are the ones that are problematic as to whether or not they're significant or not. In this second example, we have a number that contains a 0. If the 0 is in between non-zero digits, then that 0 must be significant. So, in this case, they're both the 6, the 0, and the 7 are all significant. This number has 3 significant digits or figures. If the first digit is a 0 in the number. Okay, this might happen for some reason the number might be fairly small. Those zeros are simply placeholders, and placeholders are not significant digits, and so we would not count them. But zeros that are to the right of non-zero digits are significant. So, as an example, we have a number that is 0.0036. In this particular case, the zeros that are to the left of the 3 are simply placeholders and are not significant digits. So the 3 and the 6 are the only significant digits, so there are 2 sig figs in this particular number. On the other hand, if we had a number which is 0.00360, again, the zeros to the left of the 3 are not significant, but the 0 that is to the right of the 6 is a significant digit. It has been measured, that is the estimated digit, and so this number would have 3 significant digits. Now, another little bit of ambiguity that arises is whether or not you have a number with a decimal point present. If you have a number with the decimal point present, that can have a different number of significant digits than if the decimal point is not present. In the example that's given here, we have 300 without a decimal point. In this particular case, there is only 1 significant digit, and it's implied that it's plus or minus 1 in the hundreds place. So this number actually could be as high as 400 or as low as 200. There's a lot of error associated with this estimated value. This could be compared to 300 with a decimal point. In this particular case, there are 3 significant digits, and the estimated digit is in the ones place. This number could be as high as 301 or possibly as low as 299. So it turns out that if you put a line underneath the final 0 in a 300 without a decimal point, that implies that that is the estimated digit and would imply there are 3 significant digits. There are two basic rules for how to handle significant digits in calculations. The perhaps simplest of the two rules involves calculations involving multiplication and division. If you determine the number of significant digits in the two numbers that are going to be involved in the calculation, or possibly more numbers than that, the number with the fewest number of significant digits is the one that determines how many significant digits will be in the answer. As an example, we have two numbers that we want to multiply together. The first number is 12.512. All of those are non-zero digits, so this happens to have 5 sig figs in it. The second number, 5.1, only has 2 significant digits. If we were to multiply these two numbers together, you could put that into your calculator. The calculator will spit out a bunch of digits, but some of them will not be significant digits, okay? And we have to be smarter than the calculator. Since the 5.1 only had 2 significant digits, the answer can only have 2 significant digits. So therefore, the answer will have the estimated value in the ones place, or it's the 3. We also then see that the digit just to the right of that is greater than 5, so we have to follow the rounding rules. And so in this particular case, reporting the answer will be 64 with 2 significant digits. And it's implied that the value could be 65, as high as 65, or as low as 63, and that range of error encompasses the number that we use to figure out the answer. The second rule for dealing with calculations involves additions and subtractions. Okay? In this case, we have to compare decimal places, and the estimated value that is in common with the two numbers is the one that determines the number of significant digits in the answer. So, if we want to do an example where we add the first two and subtract the last two numbers that we have here, all right, we see that the first number has a total of 5 significant digits, 13.632. The second number has 3 significant digits, it's 9.83, and the third number only has 2 significant digits, 3.1. What we want to do is compare all 3 of these numbers, finding the decimal point that has the least significance in common with all 3 numbers. In this particular case, you can see that the 3.1 has a digit in the tenths place, but does not have a digit in the hundredths place, whereas the other 2 values do have numbers in the hundredths place. Well, that means that our answer can't have a digit any further to the right than the hundredths place. So we take out our handy dandy calculator, we do the calculation carrying along all of the digits, but recognize that the tenths place in our answer is the estimated value, and so we draw a line underneath that. We see that the number just to the right of the 3 is greater than 5, so hence we have to round the 3 up to 4, and our final answer is 20.4 with 3 significant digits. It turns out that it is possible to gain and lose significant digits when one does addition and subtraction. Okay, so it turns out that rounding is a really important thing to take into account, and by convention, one could take and do rounding steps at each step of a calculation, or one could save the rounding until the end of a series of calculations. And we recommend the latter. That will minimize any kind of error associated with various types of calculations. So the general rule is that if the digit just to the right of the estimated digit is 5 or greater, you're going to round up. If it's 4 or less, you're going to round down. And so, for example, in this case, we have 6.73948. This wants to be rounded such that we only have 4 significant digits. The 6 is a sig fig, the 7 is a sig fig, the 3 is a sig fig, the 9 is a sig fig, but the 4 is the first insignificant digit, and it is less than 5, so hence this number will be, when we do the appropriate rounding, will be 6.739. If the digit is greater than 5, then we will round up. So in this case, we have 0.249. We want to round this to 2 significant digits. Remember, the 0 to the left of the decimal place is simply a placeholder. So the 0 is not a sig fig. The 2 is a sig fig, and the 4 is a sig fig. The 9 is an insignificant digit, and it is the one that's going to determine the rounding. It's greater than 5, so we will need to round the 4 up, and so our answer will be 0.25.